Astronomy. I. Introduction. Astronomy, study of the universe and the celestial bodies, gas, and dust within it. Astronomy includes observations and theories about the solar system, the stars, the galaxies, and the general structure of space. Astronomy also includes cosmology, the study of the universe and its past and future. People who study astronomy are called astronomers, and they use a wide variety of methods to perform their research. These methods usually involve ideas of physics, so most astronomers are also astrophysicists, and the terms astronomer and astrophysicist are basically identical. Some areas of astronomy also use techniques of chemistry, geology, and biology. Astronomy is the oldest science, dating back thousands of years to when primitive people noticed objects in the sky overhead and watched the way the objects moved. In ancient Egypt, the first appearance of certain stars each year marked the onset of the seasonal flood, an important event for agriculture. In 17th century England, astronomy provided methods of keeping track of time that were especially useful for accurate navigation. Astronomy has a long tradition of practical results, such as our current understanding of the stars, day and night, the seasons, and the phases of the moon. Much of today's research in astronomy does not address immediate practical problems. Instead, it involves basic research to satisfy our curiosity about the universe and the objects in it. One day such knowledge may well be of practical use to humans. See also History of Astronomy. 2. Amateur astronomy. Astronomers use tools such as telescopes, cameras, spectrographs, and computers to analyze the light that astronomical objects emit. Amateur astronomers observe the sky as a hobby, while professional astronomers are paid for their research and usually work for large institutions such as colleges, universities, observatories, and government research institutes. Amateur astronomers make valuable observations, but are often limited by lack of access to the powerful and expensive equipment of professional astronomers. A wide range of astronomical objects is accessible to amateur astronomers. Many solar system objects such as planets, moons, and comets are bright enough to be visible through binoculars and small telescopes. Small telescopes are also sufficient to reveal some of the beautiful detail in nebulous clouds of gas and dust in our Milky Way galaxy. Many amateur astronomers observe and photograph these objects. The increasing availability of sophisticated electronic instruments and computers over the past few decades has made powerful equipment more affordable and allowed amateur astronomers to expand their observations to much fainter objects. Amateur astronomers sometimes share their observations by posting their photographs on the World Wide Web, a network of information based on connections between computers. Amateurs often undertake projects that require numerous observations over days, weeks, months, or even years. By searching the sky over a long period of time, amateur astronomers may observe things in the sky that represent sudden change, such as new comets or novas, stars that brighten suddenly. This type of consistent observation is also useful for studying objects that change slowly over time, such as variable stars and double stars. Amateur astronomers observe meteor showers, sunspots, and groupings of planets and the moon in the sky. They also participate in expeditions to places in which special astronomical events such as solar eclipses and meteor showers are most visible. Several organizations, such as the Astronomical League and the American Association of Variable Star Observers, provide meetings and publications through which amateur astronomers can communicate and share their observations. 3. How astronomers work. Professional astronomers usually have access to powerful telescopes, detectors, and computers. Most work in astronomy includes 3 parts, or phases. Astronomers first observe astronomical objects by guiding telescopes and instruments to collect the appropriate information. Astronomers then analyze the images and data. After the analysis, they compare their results with existing theories to determine whether their observations match with what theories predict, or whether the theories can be improved. Some astronomers work solely on observation and analysis, and some work solely on developing new theories. Astronomy is such a broad topic that astronomers specialize in one or more parts of the field. For example, the study of the solar system is a different area of specialization than the study of stars. Astronomers who study our galaxy, the Milky Way, often use techniques different from those used by astronomers who study distant galaxies. Many planetary astronomers, such as scientists who study Mars, may have geology backgrounds and not consider themselves astronomers at all. Solar astronomers use different telescopes than nighttime astronomers use, because the sun is so bright. Theoretical astronomers may never use telescopes at all. Instead, these astronomers use existing data or sometimes only previous theoretical results to develop and test theories. An increasing field of astronomy is computational astronomy, in which astronomers use computers to simulate astronomical events. Examples of events for which simulations are useful include the formation of the earliest galaxies of the universe or the explosion of a star to make a supernova. Astronomers learn about astronomical objects by observing the energy they emit. These objects emit energy in the form of electromagnetic radiation. This radiation travels throughout the universe in the form of waves and can range from gamma rays, which have extremely short wavelengths, to visible light, to radio waves, which are very long. The entire range of these different wavelengths makes up the electromagnetic spectrum. Astronomers gather different wavelengths of electromagnetic radiation depending on the objects that are being studied. The techniques of astronomy are often very different for studying different wavelengths. Conventional telescopes work only for visible light and the parts of the spectrum near visible light, such as the shortest infrared wavelengths and the longest ultraviolet wavelengths. Earth's atmosphere complicates studies by absorbing many wavelengths of the electromagnetic spectrum. Gamma-ray astronomy, X-ray astronomy, infrared astronomy, ultraviolet astronomy, radio astronomy, visible light astronomy, cosmic ray astronomy, gravitational wave astronomy, and neutrino astronomy all use different instruments and techniques. A. Observation. Observational astronomers use telescopes or other instruments to observe the heavens. The astronomers who do the most observing, however, probably spend more time using computers than they do using telescopes. A few nights of observing with a telescope often provide enough data to keep astronomers busy for months analyzing the data. 1. Optical astronomy. Until the 20th century, all observational astronomers studied the visible light that astronomical objects emit. Such astronomers are called optical astronomers, because they observe the same part of the electromagnetic spectrum that the human eye sees. Optical astronomers use telescopes and imaging equipment to study light from objects. Professional astronomers today hardly ever actually look through telescopes. Instead, a telescope sends an object's light to a photographic plate or to an electronic light-sensitive computer chip called a charge-coupled device, or CCD. CCDs are about 50 times more sensitive than film, so today's astronomers can record in a minute an image that would have taken about an hour to record on film. Telescopes may use either lenses or mirrors to gather visible light, permitting direct observation or photographic recording of distant objects. Those that use lenses are called refracting telescopes, since they use the property of refraction, or bending, of light. See optics, reflection and refraction. The largest refracting telescope is the 40-in, 1M, telescope at the Yerkes Observatory in Williams Bay, Wisconsin, founded in the late 19th century. Lenses bend different colors of light by different amounts, so different colors focus slightly differently. Images produced by large lenses can be tinged with color, often limiting the observations to those made through filters. Filters limit the image to one color of light, so the lens bends all of the light in the image the same amount and makes the image more accurate than an image that includes all colors of light. Also, because light must pass through lenses, lenses can only be supported at the very edges. Large, heavy lenses are so thick that all the large telescopes in current use are made with other techniques. Reflecting telescopes, which use mirrors, are easier to make than refracting telescopes and reflect all colors of light equally. All the largest telescopes today are reflecting telescopes. The largest single telescopes are the Keck telescopes at Mauna Kea Observatory in Hawaii. The Keck telescope mirrors are 394 in, 10.0 m, in diameter. Mauna Kea Observatory, at an altitude of 4,205 meters 13,796 feet, is especially high. The air at the observatory is very clear, so many major telescope projects are located there. The Hubble Space Telescope, HST, a reflecting telescope that orbits Earth, has returned the clearest images of any optical telescope. The main mirror of the HST is only 94 in, 2.4 m, across, far smaller than that of the largest ground-based reflecting telescopes. Turbulence in the atmosphere makes observing objects as clearly as the HST can see impossible for ground-based telescopes. HST images of visible light are about 5 times finer than any produced by ground-based telescopes. Giant telescopes on Earth, however, collect much more light than the HST can. Examples of such giant telescopes include the twin 32 feet 10 meters Keck telescopes in Hawaii and the 426 feet 8 meters telescopes in the Very Large Telescope Array in the Atacama Desert in northern Chile. The nearest city is Antofagasta, Chile. Often astronomers use space and ground-based telescopes in conjunction. See also Space Telescope. Astronomers usually share telescopes. Many institutions with large telescopes accept applications from any astronomer who wishes to use the instruments, though others have limited sets of eligible applicants. The institution then divides the available time among successful applicants and assigns each astronomer an observing period. Astronomers can collect data from telescopes remotely. Data from Earth-based telescopes can be sent electronically over computer networks. Data from space-based telescopes reach Earth through radio waves collected by antennas on the ground. 2. Gamma-ray and X-ray astronomy. Gamma rays have the shortest wavelengths. Special telescopes in orbit around Earth, such as the National Aeronautics and Space Administration's, NASA's, Compton Gamma Ray Observatory, gather gamma rays before Earth's atmosphere absorbs them. X-rays, the next shortest wavelengths, also must be observed from space. NASA's Chandra X-ray Observatory, CXO, is a school bus-sized spacecraft that began studying X-rays from orbit in 1999. See also gamma ray astronomy, X-ray astronomy. 3. Ultraviolet astronomy. Ultraviolet light has wavelengths longer than X-rays, but shorter than visible light. Ultraviolet telescopes are similar to visible light telescopes in the way they gather light, but the atmosphere blocks most ultraviolet radiation. Most ultraviolet observations, therefore, must also take place in space. Most of the instruments on the Hubble Space Telescope, HST, are sensitive to ultraviolet radiation. See ultraviolet astronomy. Humans cannot see ultraviolet radiation, but astronomers can create visual images from ultraviolet light by assigning particular colors or shades to different intensities of radiation.